I'm glad to present. I'm glad to present our next speaker, Andriiana Plakosh from Kiev Institute of Mathematics, and she will talk about representation cohomology of alternative group of degree 4. Please, Andriiana.
Thank you. Thank you, Pantaras. Oh, thank you. Good afternoon, dear participants and organizers of conference. I'm really pleased and thankful for opportunity to be part of this conference. And I will tell you today about representation and cohomologies of the alternative group of degree 4, and it is joint work with Yuri and Drost. So,
I am sorry, Andriiana, I'm really sorry. Professor Bana, could you please stop share the presentation of our speaker, and could you please, thank you very much. Thank you very much. Okay, now.
Can I start? Yeah?
Yes, yes, great, thank you.
I will try to be short, but I have a little bit too long presentation, so I will try to make a talk in time. So, in paper, unimodal representations of alternative group of degree 4, Nazarova Lyudmila describes two-adic representations of type of the alternative group A4 of order 4, and unfortunately it was very difficult to use this description for our other purposes, such as calculation cohomology. So we propose another approach with Yuri and Tolich. It's analogous to the study of representation cohomologies of the Kleinian 4 group in our paper. So we use the techniques of Backstrom orders from works of Ringel and Rogenkamp, and thus relate the description of two-adic representations of A4 with representations of a valued graph. And it allows to completely describe the Auslander Rayton transform of this giver of two-adic representation, and the Auslander Rayton transform in this case coincides with Syzygy. It gives almost immediately the values of all Tate cohomologies of two-adic A4 lattices, since three-adic representations of A4 are very simple, and we also describe all integer representations and their cohomologies. And note that knowing cohomologies is important for application, such as classification of crystallographic groups and Chernikoff's groups. So let's G, its alternative group of order 4, and its Kleinian subgroup, and H is a factor group G by N. So we denote by A the group ring of G and set AP as the p-adic competition of A, and QA is the rational envelope of A. By A lat, or a P lat, we denote by the category of A lattices or A modulus M, such that as a group, M is a free abelian group of finite rank, respectively free ZP module of finite rank. So for n A lattices M, we also denote QM as a rational envelope of M, MP as a product, and note that QMP is a morphic to next product M by QP. So the ring A can be considered as a crossed product K by H, where K is Zn and H on. Oh, sorry. Yeah, okay, it's okay. And H naturally acts on K by conjugation. Here QK is 4 times Q, and we have a basis E1, EA, EB, and EC, where it's on the screen, you can see under this identification KP is 4 times ZP, and if P not 2, ZK2 embeds into Z2 4 times, so that ABC identifies respectively with the elements which we can see, and the action of H is trivial on the first component of QK and cyclically permutes the other 3 of them. So hence we have some big isomorphism with products, and in this isomorphic equation, theta is a primitive cubic root of 1, and if p not 2 and not 3, then we have a product AP that's product of 3 of 3 modules, so irreducible lattices in our case. And if P is equal 3, that A3 is a product of 2 lattices, Z3H and mat on 3Z3. So all the decomposable AP lattices for P not 2 and not 3 are irreducible lattices, 4 irreducible lattices, or I'm sorry, 3. ZP, ZP theta, and IP, which is 3 times ZP. And for A3, there is one more indecomposable lattice, Z3H. So in the case when P is equal to, it's quite different case, since that 2K is no more maximal order, so that every group ring R is Gorensteinian. So injection dimension R under R is 1. Therefore, all non-projective RP lattices are actually lattices over the ring R plus. And we know that order of H is invertible in Z2 for the cross product A2. And we have that radical A2 is a cross product radical K by H, and A plus is the cross product K plus by H. So note that K plus is a backstream order in sense of Ringel-Rogenkamp, and it means that there is a hereditary order K with tilde such that K embeds in K plus, and K plus is in radical K with tilde that equals a radical K plus. So in our case, K tilde is 4 times Z2, and K plus it's some sets of 4 elements, which is by module 2 is equal. So, and as A tilde is cross product K tilde by H is also hereditary, so A plus is also backstream order. So we have namely that A with tilde is isomorphic to the sum and cross and product of Z to the 2 theta and set of matrices. And one can easily see that A plus embeds into A tilde as a subring of triple x1, x2, and x3, where each of x's is from our summons from A tilde, and we have some equations for it, where rho denotes the regular representations or representation of Z2 theta. Oh, so you can see on the screen, yeah? Can I? Oh, I can show you. Okay. So, and we denote by L1, L2, L3 irreducible A tilde lattices belonging respectively to the components of the sum, and by P1 and P2 is decomposable projective A plus lattices. Pi is a product of A plus by AE, where A1 we know, A2 is 1 minus A1. So, and the only decomposable A2 lattices, there are not A plus lattices, and BI is A2 by EI. They are bijective, both projective and injective in exact category A2 lat. So, and recall that representations of backstream order are classified by representations of weighted graph gamma in sense Dalb of Andringel, and namely the vertices of gamma is one-to-one correspondence with the simple components of semi-simple algebras. So in our case we have some cross product, which give us some isomorphism, A with head, it's not head, with it's not head, it's oh, sorry, A with bar is isomorphic to product F2 by F4, and A with bar prime is isomorphic to product F2 by F4 by matrices 3 on under F2. So, hence the corresponding graph gamma with operations of type F with tilde 4, 1 is like you can see on the screen, is our graph, and 1, 2, and 3 points correspond respectively to the components F2 and F4 and matrices of A bar prime, while 1 prime and 2 prime correspond respectively to the components F2 and F4 of A bar. The weights of all arrows except gamma 2 are 1, 1, so we do not write them. Yeah. And representations of gamma, zeros, alpha, gamma 1 correspond to matrices with integers from F2, and arrows gamma 2 beta corresponds to matrices with integers from F4, and the vector dimension of representation M of gamma we denote by the next, you can see D1, D2 with primes, and D1, D3, D2. Recall that the A plus lattice M corresponding to representation V of this graph in the pre-image. When we have M tilde is such direct sum with where L1, L3, L2 we take by D1 times, D3 times, and D2 times of image phi, and phi about where we by this rule give and give by the matrix you can see on the screen, and we identify this product. This direct sum with factor M by 2M with tildes. So, the standard right-hand giver of the category representations of graph gamma consist pre-projective, pre-injective, and regular components, and when we pass to representations of backstream orders, we have to glue the pre-projective and pre-injective component into the component which we will call principal. Namely, we omit simple injective and simple projective models, and then add arrows from the remaining injective to the remaining projective. So I will show you as a result, the principal component for the order of A plus becomes like this, about L and P we was talking before. And here by MK, we denote the case our standard right-hand transform tau km of the lattices M over the ring K2 as shown in Uren-Tolch-Drost paper rejection lemma. MK is isomorphic to case Syzygy of M as of A2 model, and Pi1 are just injective Laplace lattices, those dual to projective ones, or the same injective in the exact category Laplace lat. Actually, Pi is a unique minimal over model, and Pi1 is a unique maximal submodel of Bi. And recall that Bi are the only decomposable A2 lattice which are not A plus lattice, and they are bijective, but projective and injective in A2 lattice. And note that also the other reducible A plus lattices are L1 with index plus or minus 1. Just as L3, they belong to the component matrix. Matrix, yeah, okay. I switch the time. So the dimensions of the corresponding representations of graph gamma are given by the next diagram you can see on the screen, and note that the symmetry with respect to the central dotted column, this central dotted column, corresponds to the duality from M to M with okay, in the category of A2 lattices, and the regular components for A plus lattices are the same as those for the graph gamma, and they consist of homogeneous tubes TF corresponding to monic irreducible polynomials from F2 except T minus 1. and the square plus t plus 1. And two special tubes, T1 and T0, the homogeneous tubes are of the form you can see on the screen. In these components are the Auslander-Rayton transform of the same, the syzygy X trivially, and the dimensions of representation of gamma correspond to T Kf is the next one, where D is the degree of polynomial f. So, and the special tubes have the next form, this first one and second, yeah, and dimension of all of the corresponding representations of gamma for this, for all these tubes. So, our standard Rayton transform of the same syzygy X, and there we can now go to the globalization. It will be a little bit too many information, but for describing the composable A lattices, we use following results from paper Fadeev. So these results, if MP is a P lattice is given for all prime P, so there is an A lattice M such that we have isomorphism with M between MP and MP for all P if and only if there is a QA model V such that we have isomorphic to this product for all P, and then we say that all MP are of the same rational type. So, and such lattice M is decomposable if and only if there are direct summands NP of every MP such that all NP are of the same rational type. So, in particular, if M prime is another lattice with the same localization, M and M prime decompose simultaneously. So, they say the two A lattices M and N prime are of the same genus if MP is isomorphic to MP prime for all P, as A is embeds into 6A with tilde. It's the following result from a paper Fusion Tolch Drost Adels in integral representations. So, sorry. Not that if P not 2 and not 3, for every QA model V, there is a unique P lattice L such that QL is isomorphic to some product Q by V. And therefore, an A lattice is completely defined by its two-adic and three-adic localization. And if P is 2 or 3, every QAP model, if is of the form of product QP by V under Q, and where V is a QA model, we decompose in such direct sum where R1, R2, and R3 we need in the future. W is the unique simple matrix 3Q model, and we write RTMP and call its triple rational type of MP, and hence an A lattice is defined by pair M2, M3 of lattices over A2 and A3, which are of the same rational type. So R1, R2, and R3, it's how many times we take Q, theta, and W in our direct sum. Yeah, and we will use it lately. So, and note that the unique decomposable S3 lattice, which is not reducible, is the lattice A, and the rational type of A is 1, 1, 0. From now, let M be a lattice of rational type D1, D2, D3, and M3 is equal to the sum with K1, K2, K3 and K's, how many times we took every of these summands, where L3 is the irreducible matrix 3 under Z3 lattice, and not the dimension of the corresponding representation of the valid graph gamma is the next one, D1 and D2 with primes, and d1, d3, d4 for some d1 and d2 with primes. And proposition 1 means that we have some equations to be true. K1 plus k is d1, k2 plus k is d2, and k3 is d3. And it implies the composition of a lattice M such that M2 is decomposable. And we have a theorem 3 where N is decomposable at 2 lattice, and rational type of N C1, C2, C3, and C tilde is minimum between C1 and C2. So we have that N3K is isomorphic to some sum of some direct sum of our summands, yes, and every lattice M such that M2 is isomorphic to N, isomorphic to one of N Ks, yes. And M2 we will define as a direct sum of Ni, where S is more direct sum from 1 to S, where S is more than 1, and rational type of Ni is C1 to 3 with I indexes. And Ci with tilde is minimum between C1i and C2i. And the following result is obvious, that if K is less than sum of Ci with tilde, then M decomposes in that direct sum, where ME2 is N y MM3I is AK is like this direct product, a direct sum from 4 summands, where BI are arbitrary integers such that BI is less than CI with tilde, and K is the sum of BIs. Yes, and if we from now, we suppose that K is more than sum of CIs with tilde. So if N is a direct summand of A2 of rational type, then M has a direct summand M prime such that M prime 2 is isomorphic to N, and M3 is isomorphic to sum of AC and L3. Therefore, in M is decomposable. M2 has no proper direct summand of rational type of CC and C3. In what follows, we always suppose these conditions satisfied. So if C1i is less than C2i for all I, or C1i is bigger than C2i for all I, then M decomposes. So, and the propositions which we see imply a description of a decomposable lattice M such that M2 has 2 decomposable components. If M is decomposable and S is equal to, then up to the permutation of N and 2, C11 is less than C21 and C12 is bigger than C22. There are C plus C tilde lattices where C tilde is equal to C tilde 1 and plus C tilde 2, and C plus is equal to minimum between C, this sum, corresponding to decomposition M3, where K is between C tilde and C plus. So, and the description of Tedix lattices shows that when model of I'm sorry, isn't it? I forgot. I'm sorry, difference. I forgot the word difference. I'm sorry. The model of difference is less than 2, and if all differences is 1, then proposition 5 implies that M contains a direct summand M prime, such that M prime 2 is isomorphic to a direct sum of an I and an Y and then G for some E not equal G. And the same holds if our difference between C1i and C2i is 2. Hence, we can suppose how that there is one I such that C1i minus C2i is 2, and C2g minus C1g is 4 for all G not equal I. Then proposition 5 implies that if M is decomposable, there are at most two such indexes G. One immediately sees that the unique possibility with two such indices is when M3 is isomorphic to the product direct sum of AK ln L3, where K is the sum of C1 to 3 with tilde and 2. So, and thus we have described all decomposable A lattices M with decomposable M2. So here we can see N1 and 2 with up indexes and 1 and 2 with low indexes, and is a set of decomposable lattices such that in first two items we have C1 minus C2 is 1, C1 minus C2 is 2, and in the second two items is C2 minus C1 is 1 and C2 minus C1 is 1. So then the only possibility for decomposable A lattices M such that M2 is decomposable are the following. We have three possibilities, and here you can see that our M2 decompose in a sum of two direct summands, and M3 it's A with C1 plus C2 plus 1 times. So, and you can see it's all our decomposition of the I lattices. So I will maybe end with this because my time is almost, it's almost, I have a time for one or two questions, Thank you for listening my talk, and
okay, thank you